Hi everyone, I'm Mr. Furlong, and today we're talking populations. A good place to start about talking about populations is first defining it. We can say that a population is a group of individuals of the same species that live in the same area at the same time. Here we see in this picture, there are several different species. They're all living at the same area. They're living at the same time, but we would say that there's many different populations here. For instance, we see some zebras and some giraffes and gazelles. All of those are their own individual populations. We often will study populations in a particular area. Looking at the population of a particular species on the planet is just way too big. And so we'll focus on one small area. Say the population of deer in Ohio, for instance, instead of looking at the population of deer in the United States. It's much easier to study smaller populations than it is larger populations. Now, populations, though, are changing all the time, and we can measure this by looking at their growth rate. The growth rate determines if a population is increasing, decreasing, or staying the same. There are several things that can cause populations to increase or decrease. Let's take a look at some of these factors. First of all, there is a mortality rate. So individuals will die, and the mortality rate is how many deaths occurred in that population over a period of time. Individuals are also being born. That is known as the natality rate, how many births happen in that population over time. And if we were just looking at the population of a species on the planet, really this is the only two things that we need to know. How many individuals are being born, how many are dying. But again, we study populations in smaller groups. That means that populations can change if new individuals move into or leave an area. So we also have to take a look at the immigration rate. How many individuals are moving into that area? So for instance, if we were going to take a look at the population of deer in Wood County, Ohio, it would change on a daily basis because some deer might be moving across county lines, and then you guessed it, others are going to be moving out of county lines. And so we would say that they would be emigrating. How many individuals are leaving an area? So these four things will help us to determine what the rate of change will be in a population. So populations certainly are changing. Let's take a look at some data from Ohio. Here is the skunk relative abundance from 1990 to 2011 in Ohio. And we can see that there are some years, like in the early 90s, where the population of skunks were higher. It decreased for a time, it went up for a little bit, and we can see that it's sort of remaining unchanged over the last few years. Now this is looking at a fairly large area though. We're looking at the size of the state of Ohio. We can also take a look at the size of these skunks by county. And so here we can see that in some counties they're fairly low, especially in counties where there might be some major cities like Toledo and Cleveland and Cincinnati. But in more rural areas we might see a higher population of skunks. So for instance, here we see in good old Wood County, we are in the high range for skunk populations. Now the environment can limit how big a population can get. These are what are called limiting factors, which is any biotic or abiotic factor that can affect the growth of a population. There are several different kinds of limiting factors. In fact, we can kind of break them down into two types. The first are called density-dependent factors. So what we mean by density is how many individuals are in that area. If there's a lot of individuals in that area, the density is higher. If there's fewer individuals, the density is going to be lower. A density-dependent factor really is going to only affect large populations. They don't have much effect on small populations. When the populations do get too large, there are certain factors that can affect how the population is going to grow. Some examples of these are the amount of space that's available. Some organisms require a large area. They might be measured in acres. Others might be measured in inches. We take a look at the amount of water that's available. Certainly all organisms need to have water. If you live in an area that doesn't get much moisture, you might not be able to support a large population. We look at how much food is available. If there's not enough plants for there to support a large herbivore population, that herbivore population is going to be a little bit smaller, which also then means that if you have fewer herbivores, you're going to have fewer carnivores as well. Also, disease can affect population sizes, especially in the larger population. A disease can spread a lot faster in a large population than it can in a smaller population. Let's take a look at an example of one of these. Here we are, way down here in northwest Ohio. But let's go on a trip. And we're going all the way up here into Lake Superior. This is known as Isle Royale. Back in 1959, we had an extremely cold winter, and part of Lake Superior froze all the way over to the island. Well, there had been a population, a very large population of moose that lived on this island, but then a small pack of wolves crossed over. When springtime came and the ice melted, the wolves had no way of getting back to the mainland, so they lived there, and their descendants are still there today. One of the foods that the wolves would eat, of course, would be moose. And so we see that there's a relationship that was set up between the number of moose that was available and the number of wolves on this island. Let's look at this data. This is from 1959, the year that the wolves wandered over to the island, all the way up through 2013. That there was originally 20 wolves that were on the island. Now notice your y-axis here. We have 10, 20, 30, 40, 50. That represents the wolves. Over here we have 500, 1,000, 1,500. That represents the moose. So when we take a look at the moose in 1959, they were approximately 500 on the island. Since there was plenty of moose to eat, the wolf population started to increase, which kept the moose population fairly constant. Although when the wolf population started to decrease here in the 1960s, notice what happened to the moose population. The moose population started to go up. Once the wolf population started increasing during the 70s, notice what happened to the moose population. It goes down. Around 1981, however, there was a virus that hit the wolves. They went from a high of about 50 in 1 year, dropped down to about 13 wolves. Now, what happened then, of course, is that the moose population skyrocketed. It went up to about 2,500 moose. It took a while then for the wolf population to get back to its normal numbers into the 20s and 30s. But now we're seeing a lot of inbreeding in the wolves, and the wolf population is decreasing dramatically. In fact, in the last year that we have data, 2015, there's only 3 wolves left on this island. So a lot of interesting things happening and taking place here. Our second type of limiting factor is a density-independent factor. And in this type, these factors can affect any size population. It doesn't matter whether it's really big or really small. So for example, there can be some unusual weather. Hurricanes, for instance, that might kill some individuals. If it's a small population, it might even get rid of that whole population. Natural disasters, things like earthquakes and forest fires certainly will affect the population of an area. Human activities, when humans come in and we start building homes in areas that were natural habitats for some animals, their populations might start to decline because of that. And we're now beginning to see how climate change is starting to affect populations as well. That as the climate changes, that they simply can't survive in those new conditions. Let's take a look at how populations can grow. There are 2 models to help explain this. One is called exponential growth. And in exponential growth, each generation gets larger than the previous one. And the larger the population gets, the faster it then grows. So we literally have a population explosion taking place here. Let's show this on a graph. Over time, we can see that the populations may tend to remain the same, but eventually it just goes up almost straight up on this graph. In fact, it's going off our screen right here. This is what's known as a J-curve graph. Now this can certainly happen if there's plenty of resources that's available. We have plenty of space and food and water, but the reality is that populations can't simply continue to grow exponentially like this. What we see more often is a logistic growth pattern, where because populations just simply can't continue to grow unchecked, they're going to level off at some point. And when they level off, we say that the population rate will drop down to 0. Now note, we're saying that the rate is dropping down to 0, not the population. So the population can still be high. All we're saying is that the population is not getting any bigger. It's simply staying the same. And so if we were to graph this, we would see that we might see some stable growth, and then we might even see some exponential growth. But eventually it does level off at some point. This is what's known as an S-curve. And where it levels off is known as the carrying capacity for that ecosystem. So real quick, a carrying capacity is simply the greatest number of individuals that a space can support indefinitely without degrading the environment. With populations that have gone past their carrying capacities, we often see something like this taking place, where we see that exponential growth. It just continues to go up. It goes well beyond their carrying capacity, and it might be able to stay there for a while. But what happens every time is, because the environment has been degraded, the population just crashes. And sometimes it goes all the way down to 0 individuals in that population. These are some of the things that we have to take note of as we talk about human populations. What is the carrying capacity for humans on this planet? This is something that we'll take a look at here in a future activity. Well, I hope that shed some light on population growth, and I'll see you in class.